Hello everyone, it's been a while. Today I'll be talking about how I upgraded my particle simulation from the first video, so if you didn't see it, go and watch that now. But before we start, thank you all so much for clicking on part 1. I'm just in utter disbelief because I never expected to get picked up by the algorithm at all. Not to mention, in my first ever proper video. Seriously, even Pezza commented on that. Man has 150k subs. It's just insane. So yeah, thank you all so much. Your support is invaluable, and I'll keep making these types of videos every few months. With that said, let's recap. In part 1, we managed to create a successful particle simulation using grid hashing that is able to run around 3000 particles at 60 frames per second, with 8 substeps per frame, which means around 480 Hz. I have 3 goals I'd like to achieve for this video, so let's go through them. 1 is to optimize the simulation further by changing up our grid hashing from previously, and then using multithreading. 2, to generate images using our particles. 3, to add obstacles in the form of rectangles and circles to have a more fun way of interacting with them. As you recall, in the first video we used grid hashing to speed up our simulation. We did this by slicing the window into a large grid to store the particles in each cell, which eliminated the need to check collisions between particles that are far apart from each other and only look at neighboring cells for each particle, like so. To make things easier for us, it's time for some code housekeeping. We stored the full particle object in our grid back then, but I've come to the realization that we just need to store the index numbers of each particle, which saves us some space and time. I also moved the code for the particle structure into a separate file so I don't need to scroll as much. Finally, I'll make all the particles the same size, which should have the grid doing less work. With many particles, this won't look too bland, and will make the grid hashing faster. This is because, as we rely on only having to check neighboring cells, if we have particles of different sizes, we need to set our cell size to the maximum diameter of a particle. But since not all particles are that large, there could be more particles in a cell on average, which of course would take longer to check. Oh, and this also has the added benefit of removing this mass ratio calculation for collisions. Now, the grid hashing can be made quite a bit faster. There are 2 things we can do. First, as a commenter from the first video pointed out, we're looping over all particles, then looking at the 9 surrounding cells of that particle. Instead, we can loop over all cells and go over all the particles in that cell at once to check them with the surrounding cell, which removes some redundancy. After this change, this makes our simulation just about twice as fast, which lets us handle 6,000 particles at 60 frames per second. So, thanks for the suggestion, very cool. But wait, it gets even better. Pairs of adjacent cells are being processed twice here, which is redundant. So we can cut off 4 of our 9 cells in our search space like so. This bumps our particle performance up to 8,000 particles, which is quite excellent, I would say. Another thing that might be improved is our update of the grid each substep. Currently, we're clearing out the entire grid, then filling it back in each time. But in reality, I'm not sure if that many particles change cells at a given time step. So instead, let's just check all particles and see if we need to make any modifications to the grid. that doesn't seem much faster, and actually may slow our simulation down in the long run because of this find function. So I'll keep that for now, just to feel a little glow of accomplishment, but keep the original solution just in case. Maybe the bulk of our time is spent on other stuff, so this doesn't have that much impact. Let me know what you think the reason is. Well, that's all I can think of to upgrade our grid lookup. So let's move on. Before we add multithreading, there is one thing I really want to play around with, and that's forming an image using the particles. In theory, the simulation, if running perfectly, should be deterministic, which means if we run the simulation twice, and the particles spawn at the exact same times and velocities and positions, the particles will end up at the exact same positions both times. This means after we figure out where each particle ends up, we can apply some color to those particles, knowing where they'll end up, and form an image, just like Pezza did in his video. To test this, I moved the particle spawn position to a corner and made them all spawn in the same direction. The deterministic property we're looking for is achieved. So I then printed the positions of each particle after the simulation was stable and fed them into this little Python program using Python's image library, or PIL, to get the colors of each pixel on our image corresponding to the positions. I fed this back into the simulation like so, and voila! My YouTube banner brought to life with particles. And while the particles are filling the screen, may I direct your attention to the shiny subscribe button? Doesn't it look beautiful? Don't you just want to press it? I'll be sure to try this when we have multi-threaded tens of thousands of particles, but for now, here are a few other images that I mapped out. Okay, time to set up multi-threading. To accommodate a larger number of particles, I made the grid larger and the particles smaller. Now the plan is to make the threads manage vertical slices of cells. I found the threads very difficult to set up, mostly because I had to learn a bunch of new C++ jargon and stuff which I hadn't encountered before. It took 2 weeks with much tinkering and a slowly draining mental stability that definitely took its toll on me. I'm still scarred by the experience. This was the first time I found ChatGPT genuinely useful in helping me understand code by giving simple examples and answering all my noob questions. Now that I've finished, I can hopefully summarize this in a way someone with little to no experience, like I was, could understand. The way the threads will work is that we have some number of them running all at once, and I have a struct for an individual thread, as well as a struct to store and distribute a bunch of tasks for the threads called the task queue. Once a thread has completed its current task, it can take a new one at once from the task queue, so that's what I'm going to show first. The add task function over here looks quite scary, at least to me. But GPT advised me to use the double ampersand to denote that I have a R value. An R value is something I don't perfectly understand, but as far as I know, it's a value that doesn't really exist in memory, like a literal. So if you have int x equals 1, then that 1 is an R value. Or is it? I'm pretty sure it is. Moving on. The point is that R values let us do perfect forwarding, which means that we use move semantics to move the argument instead of copying it, saving memory. Think changing the labels on two containers instead of swapping their contents. That's what this move does. To ensure the threads don't interfere with each other, which would not let us have a good day, we use what's called a mutex, coming from mutually exclusive, which ensures that only one thread can work on the same resource, i.e. a cell, at a time. Here, this remaining tasks counter is an atomic type. This means that all operations on it are thread safe, so only one thread can operate on it at a time. This bypasses the need for mutex lock and can also make our code faster. To finish off our task queue, in the wait until done function, making a thread yield just means it'll tell the computer to not care about this thread and prioritize working on other threads in the queue. The workings of a single thread are in the thread struct, which contains a thread and a pointer to the central task queue. Each thread will continually request new tasks from the task queue, execute them, and then repeat. Threads don't always finish at the same time, as one thread could be processing a relatively empty section, and another one could be full, which would make the simulation non-deterministic. To fix this, I isolated the processes for each thread like so, slicing each region into two, and first feeding the left half to the threads, waiting till they were processed, then feeding the right half. Then I added multithreading to the border detection and the particle updates for good measure. Let's unload our multi-threaded particles. It's slower than before. This result was devastating, catastrophic, calamitous even. In the face of complete and utter defeat, I told myself to take a break. There are two types of obstacles I'd like to add, circular and rectangular. I want both to be able to move and the rectangular ones to rotate. After the demotivating turnout of multithreading, I decided to start simple. A circular or dot-shaped obstacle, as I called it, is quite easy. It's just a boring old particle whose position isn't affected by collisions or gravity. So, Command-C and Command-V later. Here's a copy of our particle class, and now I'll just take all the physics stuff out. For our movement, I added two types. The first is an oscillation between two positions, for which I used the sine function to calculate where in between the two endpoints the particles would be. The second is a basic linear interpolation where you move from a start point to an end point at a constant velocity, and then teleport back to the start point. Then, to get them in our simulation, I simply created the add, update, and collide functions in the solver. I took advantage of the grid hashing to check only the small area that the obstacle affects instead of all particles. Here are a row of dot obstacles in action. They work first try. I sure hope the rectangular obstacles will be as obedient. For the rectangular or box-shaped obstacle, let's just duplicate everything I added for the dot obstacle and give it a rename. Command-C, Command-V. Then I replaced the radius with the dimensions and gave it the property of rotation by adding variables storing the current rotation angle and the rotation speed. A box's collision is much more annoying to work with, as it has 4 edges we need to consider, plus the rotation will make the math super tedious. Or will it? Well, yes, still it'll be tedious, but probably not as much as you think. See, I'm something of a math enjoyer, and today is the day I finally cast the rotation matrix. Fight! By applying a rotation matrix, we are able to transform the entire plane around the center of the box, reverting its rotation and allowing us to compute collision for horizontal and vertical edges. Child's play. This also allows us to find the bounding box of our rectangle for use in grid hashing. Now, here I've displayed the regions that trigger a collision for each edge, and our calculations are, as you can see, relatively quite simple. After all is done, we can multiply by the inverse rotation matrix to undo our transformation. Let's test things by pulling up a massive spinning rectangle in the middle of the screen. That doesn't seem to be working. I think I found the issue. Let's try again. Oof, not that either. And once more. Oh, okay, that's looking more normal. There are 3 things that I'm noticing are being a bit funny. The first one is that as the box rotates under and away from the particles, they bounce almost nervously around. This is probably explained by how the particle falls a tiny amount as the box rotates in a frame, and then collides with the box and bounces back a tiny amount, falls, bounces again, and so on. The second funny thing is how particles closest to the obstacle sort of form a smooth path in their fall-off as the angle gets to vertical. My theory is that that's how the box works. It can't move when hit, so every frame, whatever particles that were pushed into the box by either gravity or collisions between neighboring particles are just pressed against the surface of the box, which could push the upper layers away from the bottom layer, which would stay firmly on the obstacle and cause this consistent arc. That's something I have no idea how to fix. So let's gloss over that and focus on funny number 3, the corners. There's a noticeable gap between particles over here, and the particles are really just getting launched as soon as leaving those gaps. And we might have a way to fix it. Let's go back to our collision regions. Whenever a particle's center is in the overlap between 2 regions, a corner bounce should happen. However, this is not exactly accurate. If a particle is just in this region at the very edge here, it's not touching the box. So instead, we need to reduce our bounce regions so they're in line with the edges of the box. But then, now how do we consider corner bounces? Well, as all corner bounces are off just a single point, we could imagine a tiny dot obstacle at each corner, with radius 0. We might as well write a general function, dot bounce, and use it everywhere. That works. Let's apply it and see what happens. Wonderful, the gaps are gone. There's still a noticeable curve, but that probably happens for the same reason as before. I did this section on stream, and there's another little thing that happened that you may be interested to know. To save battery, my Mac is always on low power mode. This made my stream really laggy for my viewers, so I tried turning this off, and that fixed the stream. But on a side note, my simulation sped up to allow handling of 11,000 particles. I was then able to finally put multi-threading back into the simulation, with 3 threads currently being optimal, getting to 2 to the 14th power, or 16,384 particles at 60 FPS. We just doubled our particles. But then, out of curiosity, I printed out times taken for the physics solver and the rendering. It turns out that rendering takes most of the time, and so I'd like to improve that so we can have even more particles. One way is to multi-thread the renderer. To do this, it's a good idea to bundle our thread-related stuff into one struct to make for easy access. However, as I found out, multi-threading doesn't work with our current rendering method, because we have multiple threads trying to render the same context apparently, which leads on to the second way. Based on what I've read on the documentation, calling the draw function a bunch of times isn't good for my GPU. You've probably heard that they're designed to handle triangles instead. So, SFML helpfully provides the vertex array class, which allows us to draw very basic shapes, which will be processed as triangles. Additionally, we can apply textures to these, and so I drew up myself a giant circle and used a list of quads, which I made squares, and just slapped the circle texture on it, along with a color. Ta-da! Since all the particles are really small, we don't really need the level of detail our 512 by 512 pixel circle provides, so we can generate a mipmap, which makes everything faster by making smaller and smaller copies of the image. Then I repeated this for the obstacles and finally added multithreading. I noticed most of my multi-threaded code consisted of the same structure, a calculation to figure out the range of each thread, and then the addition of all the tasks to the task queue, and then with this bit at the end to account for leftovers, and then finally this to wait until all the tasks are done. So I put all of that into a separate function inside the task queue structure, and that saves a bit of code. Finally, we can use this in our renderer and let the particles fly. I hope you enjoyed, and I'll see you in the next video. Thanks for watching.